NENOMATICA, where mathematics meets YouTube excellence. Welcome to our math video on solving quadratic equations using the perfect square identity. This method is particularly useful when we want to solve quadratic equations without using the quadratic formula. Let's start by reminding ourselves of the perfect square identity. This identity tells us that a squared plus 2, a b plus b squared equals a plus b, all squared. Now let's solve an example. We'll solve the quadratic equation x squared plus 6x plus 9 equals 0. Play button step 1. We need to recognize if our equation matches the perfect square pattern. Let's compare our equation with the perfect square identity. Looking at our equation x squared plus 6x plus 9 equals 0, we can see that it matches the pattern a squared plus 2, a b plus b squared, whereas x and b is 3. This means we can rewrite our equation as x squared plus 2 times x times 3 plus 3 squared equals 0. Let's simplify this expression. X squared plus 2 times x times 3 equals x squared plus 6x, and 3 squared equals 9. So our equation becomes x squared plus 6x plus 9 equals 0. Thinking phase, now we can apply the perfect square identity. Since x squared plus 6x plus 9 matches the pattern a squared plus 2, a b plus b squared, whereas x and b is 3, we can rewrite this as x plus 3 squared equals 0. Now we can solve for x. If x plus 3 squared equals 0, then x plus 3 equals 0, because the only number that gives 0 when squared is 0 itself. Rearranging, we get x equals negative 3. Let's verify our answer. When we substitute x equals negative 3 back into the original equation, we get negative 3 squared plus 6 times negative 3 plus 9 equals 9 minus 18 plus 9 equals 0. So x equals negative 3 is the solution to our quadratic equation. Let's recap what we did in this example. 1. We recognized that our quadratic equation matched the perfect square pattern as squared plus 2, 8b plus b squared. 2. We identified that it equals x and b equals 3. 3. We applied the perfect square identity to rewrite the left side as x plus 3 squared. 4. We used the property that if a squared equals 0, then a equals 0. 5. We solved the resulting linear equation to find that x equals negative 3. 25x squared plus 60x plus 36 equals 0. Our first step is to recognize that this equation has terms that might form a perfect square trinomial. We'll rewrite the equation to highlight this pattern. We can rewrite 25x squared as 5x quantity squared. In step 2, we can see that our equation follows the pattern a squared plus 2, a b plus b squared, which equals a plus b quantity squared. This pattern is the formula for the expansion of a perfect square binomial. In step 3, we can rewrite our equation as 5x plus 6 quantity squared equals 0. In step 4, we can use the zero product property. If a squared equals 0, then a must equals 0. So we can write 5x plus 6 times 5x plus 6 equals 0. In step 5, we solve for x. Since the product of 5x plus 6 with itself equals 0, we know that 5x plus 6 equals 0. Therefore, 5x equals negative 6, and x equals negative 6 divided by 5, which is negative 6/5. Therefore, the equation 25x squared plus 60x plus 36 equals 0 has a single solution, which is x equals negative 6/5. This is a repeated root, meaning it occurs twice in our solution. In summary, we've solved the quadratic equation using the perfect square method. This method works especially well when the quadratic can be written as a perfect square trinomial. We identified the pattern, factored it as a perfect square, and then solve for x to get our final answer. Today we'll learn how to solve a quadratic equation by recognizing a perfect square trinomial pattern. Let's look at our example. We want to solve the quadratic equation x squared plus 8x plus 16 equals 0. Step 1. We'll rewrite our equation to see if we can identify a pattern. Let's rearrange to see if this might be a perfect square trinomial. We can write this as x squared plus 2 times x times 4 plus 4 squared equals 0. Notice the pattern here. We have the square of x plus twice the product of x and 4 plus the square of 4. Step 2. Now we can apply the perfect square formula. We recognize that this follows the pattern a squared plus 2 ab plus b squared, which equals a plus b squared. In our case, A is x and b is 4. So we can rewrite our equation as x plus 4 squared equals 0. Step 3. Now we'll expand this into linear factors. If x plus 4 squared equals 0, then this means x plus 4 times x plus 4 equals 0. Step 4. Now we can solve for x using the zero product property. If a product equals 0, then at least one of the factors must equal 0. So we have x plus 4 equals 0, which gives us x equals negative 4. We also have a second equation, x plus 4 equals 0, which also gives us x equals negative 4. Since both factors are identical, we get the same solution twice. So our quadratic equation has a repeated root at x equals negative 4. Let's understand what this means graphically. When a quadratic equation has a repeated root, it means the parabola touches the x-axis exactly once at a single point. In this case, the parabola touches the x-axis at x equals negative 4. The perfect square trinomial pattern x squared plus 8x plus 16 can be written as x plus 4 squared, which cannot be negative. The only way x plus 4 squared equals 0 is when x plus 4 equals 0, giving us x equals negative 4. In conclusion, we've solved the quadratic equation x squared plus 8x plus 16 equals 0 by recognizing it as a perfect square trinomial. We identified that it follows the pattern a squared plus 2, a b plus b squared equals a plus b squared. This allowed us to directly rewrite the equation as x plus 4 squared equals 0, which gave us the repeated root x equals negative 4. When you see a quadratic equation, always check if it's a perfect square trinomial before using the quadratic formula, as it can save you time and calculations. Let's summarize what we've learned today about solving quadratic equations by recognizing perfect square trinomials. Let's start by writing down our quadratic equation. Our first step in the completing the square method is to rewrite this equation in the form of y squared plus 2 times y times some value plus the square of that value. This form follows the pattern of a perfect square trinomial. We've identified that in our equation, y is our first term, and 6 is the value that when doubled and multiplied by y gives us 12y. Also, 6 squared equals 36, which is our constant term. This confirms we can rewrite the equation in the perfect square trinomial form. Now, let's recall the algebraic identity that a squared plus 2ab plus b squared equals a plus b quantity squared. Using this identity, we can rewrite our equation. The y squared plus 12y plus 36 becomes y plus 6 quantity squared equals 0. Next, we can expand this further by writing it as y plus 6 times y plus 6 equals 0. This is to help us solve for the value of y. Now, we can use the zero product property. When a product of factors equals 0, then at least one of the factors must be 0. Applying this property to our equation, we get y plus 6 equals 0, which means y equals negative 6. And since we have the same factor twice, we get the same solution twice. Let's visualize what this means graphically. The quadratic equation, y squared plus 12y plus 36 equals 0, represents a parabola. Since we found that y equals negative 6 is a repeated solution, this means the parabola touches the x-axis at exactly one point, which is negative 6. Let's double-check our solution by substituting y equals negative 6 back into the original equation. Y squared plus 12y plus 36 equals 0. Substituting y equals negative 6. Negative 6 squared plus 12 times negative 6 plus 36. That's 36 minus 72 plus 36, which equals 0. So our solution checks out, and we've verified that y equals negative 6 is indeed the solution to our original equation. To summarize what we've learned, the completing the square method is an elegant approach to solving quadratic equations. We rewrote our expression in the form of a perfect square trinomial applied algebraic identities, and found that our equation has a repeated solution at y equals negative 6. This method is particularly useful when dealing with quadratic equations that may not easily factor using other methods. It also helps us visualize the geometric significance of our solutions. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.